welcome to this explainer. Today, we're unlocking what I like to call the ultimate chemist's toolkit. We're going to explore the invisible energy that drives reactions, figure out exactly how to perfectly synthesize chemical compounds, and learn how to tear complex mixtures apart into their fundamental pieces. Let's get right to it.
Here's our roadmap for today. We'll cover energy and chemical reactions, the science of salts, lab apparatus and solutions, and finish up with purifying and separating mixtures.
Section 1. Energy in chemical reactions. Understanding the heat.
Okay, before we even try to measure heat, we really need to understand why it's moving in the first place. You see, chemical reactions happen because elements are constantly trying to reach a more stable energy state by breaking old bonds and forming new ones. But to really grasp this energetics game, we have to draw a strict boundary. In chemistry, the universe is basically split into just two things. You've got the chemical system, that's where the actual reaction is happening, and then the surroundings. And surroundings literally means everything else. We're talking the glass beaker, the thermometer, even the air in the lab.
Now check out the sharp contrast here. Forming new bonds is an exothermic process. It literally throws thermal energy outward into the surroundings, which, you guessed it, spikes the thermometer. The reactants start out with a ton of energy, and the products end up with less. Simple enough, right? But to break bonds, a reaction must be endothermic. It aggressively steals heat from the room, causing the temperature to plummet. So in this case, the final products end up holding way more energy than the initial reactants.
And listen, this isn't just dry lab theory. This is your daily life. Every single time you snap one of those winter hand warmers or crack open a self-heating coffee can, you are literally holding a controlled exothermic reaction right in the palm of your hand. On the flip side, think about when you crack a sports cold pack for a sprained ankle. That is an endothermic reaction aggressively pulling heat right out of your swollen muscles. It's the exact same fundamental science at play in the real world.
Moving on to Section 2. The science of salts, synthesis and solubility.
So when a hydrogen ion in an acid gets replaced by a metal or an ammonium ion, you get an ionic compound that we universally call a salt. And mastering these solubility rules, it's basically a chemist's ultimate cheat sheet. For example, sodium, potassium, and ammonium salts are always soluble, no matter what. But look at the carbonates and hydroxides down there. Most of them are stubbornly insoluble. Memorizing these exact exceptions, like silver and lead chlorides, is absolutely crucial. It's the secret to predicting exactly how your synthesis is going to go. Because of those rules, chemists use a mental flowchart just like this to choose their attack plan. It's an elegant little game of balancing safe reactivity with solubility. The first question you ask, does the metal react safely with acids? If yes, boom, use the excess metal method. If no, you check if the base is soluble. If it's insoluble, you go with excess solid. But, and here's the catch, if your base is highly soluble, like sodium hydroxide, you have to pivot to a much more precise titration method. Let's actually break those methods down.
Think of method A kind of like making an overly sweet iced tea. We use this when our starting solid is insoluble. By intentionally dumping an absolute excess of our metal or base into the acid, we guarantee, and I mean guarantee, that every last drop of the dangerous acid is completely neutralized. You literally just stand there and watch until no more gas bubbles up or the solid completely stops dissolving. Once it's done, you simply filter out the leftover sludge at the bottom. What you're left with is a perfectly pure salt solution, totally ready to be evaporated.
But what about those highly soluble bases? Well, you can't just filter out the excess because it would stay dissolved and completely ruin your batch. So we pivot to method B, the titration technique. And this requires serious precision. You use a colored indicator to find the exact, painstaking, drop-by-drop neutralization point between your acid and your alkali. And here's the crazy part. Once you record the precise volumes you needed, you actually have to toss that batch out. Then, you repeat the whole experiment perfectly without the indicator, just so your final salt crystals aren't permanently dyed orange. Pretty wild, right?
All right, Section 3. Lab apparatus and solutions. Precision in practice.
Choosing the right glassware is exactly like choosing your kitchen tools. I mean, you wouldn't use a massive soup ladle to measure out a tiny teaspoon of vanilla extract, right? For quick, approximate mixing, a measuring cylinder is perfectly fine. But if you need a highly accurate, single fixed volume, you reach for a volumetric pipette. And for delivering variable fraction of a milliliter volumes, like in that painstaking titration we just talked about, the burette is your best, albeit slightly trickiest friend.
Beyond just measuring liquids, we really need to understand what's happening on a molecular level inside that beaker. When a solute fully dissolves into a solvent, you get a solution. Keep adding solute until absolutely no more can dissolve, and boom, you've hit saturation. But why does all this matter? Well, Analyzing these solutions, specifically by testing their exact melting and boiling points, acts as the ultimate chemical lie detector test. You see, a perfectly sharp, measurable melting point proves the absolute purity of a substance. It's how we ensure that our medicines and food additives contain absolutely zero harmful impurities.
And finally, Section 4, Purifying and Separating Mixtures. The final isolation.
Filtration is really our frontline defense for separating insoluble solids from liquids. Think of the filter paper as a microscopic bouncer at a club. The tiny molecules of the liquid and any dissolved substances are small enough to slip right through the door, creating the pure filtrate down at the bottom. Meanwhile, the larger, clunky, undissolved solid particles get caught up top, stuck outside as the residue.
But what if the solid is fully dissolved in the liquid, completely hiding from our bouncer? That's when we have to force it out using crystallization. First, we gently heat the solution to evaporate the solvent and concentrate it. Then, we manipulate the temperature. Because solids become much less soluble as things cool down, dropping the temperature literally forces the pure solid to crystallize right out of the liquid. It seemingly appears out of nowhere, perfectly ready to be filtered and dried.
Now let's compare simple distillation directly to a fractional column. Simple distillation easily rescues a solvent from a solution. It's like boiling pure water away from copper sulfate, turning it to steam and condensing it right back to a liquid. Super straightforward. But when you have a messy soup of multiple miscible liquids all mixed together, simple distillation just won't cut it. You have to upgrade to the fractional distillation column.
Fractional distillation relies on this strict, temperature-controlled obstacle course. As the heated mixture evaporates, the vapors rise up into a column that's packed with glass beads. And these beads act like thermal hurdles. Only the vapor that has hit its exact, specific boiling point has the energy to make it all the way to the top and into the condenser. Any unwanted liquids with higher boiling points, they lose energy, condense early on those glass beads, and fall right back down into the boiling flask.
And here's the coolest part. This exact same lab process literally runs the modern world. When scaled up to massive steel towers, fractional distillation is exactly how the petroleum industry continuously refines sticky crude oil into usable petrol and fuels. It's how we isolate pure ethanol from fermented plant sugars. We even use it to separate the very air we breathe. They literally cool atmospheric air into a liquid and then warm it back up to boil off perfectly isolated purified gases one by one. It's amazing.
All right, for our last technique, when we need to separate tiny amounts of complex soluble mixtures like food dyes or amino acids, we execute the incredibly precise steps of paper chromatography. Now, we absolutely have to draw our baseline in pencil because pen ink would just dissolve and ruin the whole experiment. We spot our mixtures, and critically, we dip the paper into a solvent bath, ensuring the liquid level starts strictly below that pencil line. If we didn't, our carefully placed spots would just wash away into the bath instead of creeping up the paper like they're supposed to.
To definitively identify those separated spots, chemists calculate the retention factor, or RF value. You just divide the distance the spot traveled by the total distance the solvent traveled. It's basically a chemical fingerprint. Because pure substances have a characteristic mathematically identifiable RF value, this exact ratio allows a chemist to identify unknown components with absolute certainty. They can even use special chemical sprays to reveal substances that are completely invisible to the naked eye.
So, after mapping out this entire chemist toolkit, we are left with a pretty fascinating question. If we can manipulate invisible energy to break bonds and perfectly isolate the resulting compounds with atomic precision, what are the true limits to the new materials, medicines, and fuels we can engineer next? Thanks so much for joining me on this explainer. Keep questioning the physical worlds around you.